Sauce here. This is a video lesson, a related rates example. I have a contextual problem here. I'm going to read, then diagram, and in my diagram, label and find relationships between the variables before I go to a solution process. A 4-foot tall person walks away from an 18-foot lamppost at 4 feet per second. At what rate is the shadow of the person changing when they are 20 feet away from the lamppost? Well, let's make sense of this context by drawing a diagram. The problem talks about a lamppost, and the lamppost is going to meet the ground at a right angle. We have a person who is walking away from the lamppost. The person is 4 feet tall. The lamppost is 18 feet tall. And the person is walking away from the lamppost, so they must have a distance from the lamppost we'll call P. And that distance P is increasing if they're walking away. I'm going to put an arrow on the line that represents that distance to suggest that there is a motion or a rate of change involved. This person makes a shadow, so the lamppost must be casting a light, and this might be evening or nighttime. So we're going to assume that the light comes from the top of the lamppost and creates a shadow by shining over the person's head down on the ground. And the length of the shadow then will be the distance between the person's position and where the light first touches the ground that's allowed to pass overhead. The shadow's length is going to change. It's implied by the problem. And so we'll give it the variable s to represent its length, and the shadow will also be increasing. This person is going to be assumed to be perpendicular to the ground. And in looking at this diagram and checking to see that I've included all information that I still have a rate. I can see that I have two triangles. They're right triangles, one small and one large. They share this angle. These variables are related, P and S, because these triangles are similar. The sides of similar triangles are proportional. So one of the many things that I could write, or one of the proportions I could write that relates P and S, is going to think of S as a side of the smaller triangle that is corresponding to the side of the larger triangle, which is P plus S. I have to add these two lengths together to get the side of the larger triangle. So proportionally, I could say the side of the smaller triangle over another of its legs that has a measure of 4 is proportional to the corresponding side to S, which is P plus S, over the side that corresponds with the side of 4, in this case 18. And I have found in my diagram an equation that relates those two variables. Let's go back to the problem. I have a rate, and this is a rate of change 4 feet per second. It's a speed at which the person's distance to the lamppost, which we've labeled P, is increasing. So part of this problem involves a value for P and a rate of change of P. The rate of change of P is given in the problem to be 4 feet per second. The value of P is given in the problem as 20 feet. when it says when they are 20 feet away from the lamppost. The other variable that's going to relate to P is S. And since this is a related rate problem, we should expect when two variables relate, then their rates of change will also be important ingredients in this problem. The rate of change of S with respect to time then completes the information that I expect to use. The question is asking about the rate, and it's the rate of change of the shadow. So it's the ds over dt that I'm looking for in a final answer. If that's the case, then I might need a value for S at this time that the person is 20 feet away. I can find a value for S by putting the known value of P into the equation that relates them. As a side problem, I'll do that. S divided by 4 is equal to the known value of 20 for P plus S divided by 18. Multiplying both sides by 18 and both sides by 4, I get 18S is equal to 4 times 20 is 80 plus 4S. Subtracting 4S from both sides, and then getting S by itself. Now, if I'm finding the rate of change of S with respect to time, I'm going to need to take the derivative of the equation that relates those variables to then introduce an equation that will have those rates within it. I'm going to modify this by multiplying both sides by 18 and both sides by 4. And I can simplify this even further. And then I'm going to take the derivative with respect to time, treating S and P as functions of time. And I get so if I'm asked to find the rate of change of S with respect to time, I have an equation for it. All I need is the rate of change of the position, which is 4. When I substitute 4 in for dp over dt, I get 14 ds over dt is equal to 4 times the value of 4 dp over dt. 4 times 4 is 16. If I divide by 14, I'll get ds over dt by itself is equal to 16 over 14. And this is a contextual problem with units. The rate of change of the position was feet per second. So was the shadow. You can see that I did an extra step of work in finding S. I could have seen that S was unnecessary. It often is necessary to have values for both of the variables as well as their derivatives. I could have seen that S wasn't going to be useful by taking the derivative of the equation that relates P and S first and then observing what it needed in order to calculate my final value. But I don't regret doing extra work in setting up what I'm expected to do with the problem, because very often related rate problems are complicated enough so that finding all the relationships you can at first helps you understand the direction that you need to take to get to the answer that the question expects.